Okay, this is the first the video that goes along with the first section of chapter 5, section 5.1, and we're dealing with angles. So before we even get to these notes, let's talk about angles, like say in geometry. So in geometry, we have two rays with a common vertex, and that would be an angle. Usually we limit that angle. So for example, that angle measure would be between 0 and 180. Now, depending on the textbook, some textbooks say less than 180 because once this angle reaches 180, then it's actually a straight line or opposing rays. A lot of books call that a straight angle. So we have something like that, and so that's 180 degrees. Now, if we were to extend that and make it bigger, so we went a little bit beyond 180, well, in geometry, we no longer call this the angle. Instead, this is the angle. So it would be less than 180, okay? So the angle could be really small, something like this. And so that's the angle, and it's pretty small, or it can be as big as 180. So I guess those would be two rays there. So you could have an angle really small, close to 0, or it can be as big as 180. Once you go past 180, you can kind of see here's the straight line. If we were to go straight, it's gone past that. And so we no longer would call that angle out there the thing that would be bigger than 180, the angle. We call this the angle, okay? But that restriction does not apply to trigonometry, okay? And we'll talk about that more in a second. An angle, first of all, just two rays that share a common endpoint. That's, this ray and that ray are going to form an angle. Now, we call this the angle in standard position. So one of its rays, so first of all, the vertex is on the origin of the xy coordinate plane. And the initial side of the angle is coincident with the x-axis. And then the terminal side is somewhere else. All right, so for example, this we talk about here, this is the measure of this angle. The vertex is here, the terminal side, and the initial side. Now, the initial side is always on the x-axis if it's in standard position, so much so that we don't generally even bother drawing in that initial side. We often will just draw in the terminal side. Okay, so this here is kind of what I was talking about before. In geometry, the angle measures were typically from 0 to 180, maybe inclusive if you called it a straight angle, but generally not bigger than 180 degrees. But in trigonometry, we can have more than that. All right, and then it can even be negative, and we'll see that in a couple of examples we do here. All right, so let's draw this, an angle in standard position that measures 90 degrees. So again, here's the initial side over here, and then 90 degrees would be up here, and so that's 90 degrees. All right, what would 135 degrees look like? So these are very what we call common angles, and we're going to be very comfortable with these in a little while after a couple of lessons. So 135 degrees would be over here in the second quadrant. So we have, again, the first quadrant, second quadrant, third quadrant, and fourth quadrant, often written with Roman numerals. So first, second, third, fourth quadrant. So it's going to be over here in the second quadrant. And so that angle is 135 degrees. You can see I didn't even draw the initial side. It's over here at 90. On the x-axis is the initial side. All right, now, negative. We have a negative angle now. So again, something in geometry that it never happened. We never had a negative angle in geometry. Wouldn't make sense. But here it is. So positive rotation is this way. Negative rotation is this way. So if we're rotating 45 degrees, so positive would be up here. but we're rotating negatively, so we're down here. And so this is the angle we're talking about. So going sort of clockwise from the x-axis. Again, here's our initial side, and the terminal side, 45 degrees, but negative 45 degrees. All right, negative 180. So here's the initial side, there's the terminal side. Okay, so both on the x-axis. So that is negative 180 degrees. All right, 270 degrees, so it's positive. So 270 degrees, we're rotating that way again. Initial side is here. And 270 degrees is 3 90s, right? So 90 makes 180, another 90 makes 270. So our terminal side is sort of the negative y-axis. All right, so negative 225 degrees. Think about which quadrant we're in. We know we're rotating this way now, right, because it's negative. So we have the initial side here. Where will the terminal side be? Well, this is 90, 180, another 45 will make 225. So it's this angle here. Okay? Terminal side there. Now notice the terminal side for negative 225 is the same as the terminal side of the angle at 135. They have what we will refer to as the same reference angle, which is this angle. That angle and that angle are the same. So the reference angle is the angle formed with the terminal side and the nearest x-axis. Okay, so 360 degrees, that's one full revolution. So that means we would go start here, rotate all the way around. And so the terminal and initial side are the same thing. 360 degrees in one full revolution. All right, so if we have some unknowns in mathematics, we often use variables. So we might say x, we might say y. But here, when the unknown or when the item we're talking about is an angle, we don't generally use like our normal alphabet. Instead, we use the Greek alphabet. So this first, it's kind of maybe hard to see. It's a like an O with a line through it. That is theta. Okay, and then we have this thing that kind of looks like a fish or almost an A. That is alpha. And then sort of a scripted sort of B with a little tail, that's beta. Okay, so alpha, beta, those are the first two letters of the Greek alphabet. And then theta is something, we often use theta for the measure of an angle or for an angle. But sometimes we'll want, maybe we have two angles, maybe we'll have three angles. So we're not going to call them all theta. Just like if you had more than one variable, you wouldn't just use x repeatedly. You would use x and y and maybe a and b or whatever. Here we can use theta, we can use alpha, we can use beta to denote three different angles. Okay. So we have here is the Greek alphabet. If any of you join, when you go to college, you join fraternities or sororities. They call it Greek life, right? And all of the sororities and fraternities have Greek letter names. Okay, so you'll at some point, if you join a fraternity or a sorority, you'll have to memorize the Greek alphabet. That's something they make you do. All right. So again, uppercase and lowercase. So the capital alpha looks a lot like our capital A. Capital beta looks a lot like our B, and so on. All right. So some of them look similar. Some of them do not. Certainly the lowercase letters do not look a lot like any of our alphabet. All right, so make sure that you're comfortable with all the following terms as they relate to angles. So what is an acute angle, a right angle, an obtuse angle, a straight angle. Complementary, supplementary. So two angles that sum to 90, we call them complementary. Two angles that the measures sum to 180, we call them supplementary. All of these are things that we will assume that you know going into these lessons, this chapter on trigonometry. So make sure that you're comfortable with those. Look in the textbook to see if you need any help with any of those. Come see me at lunch. All right, degrees. So we measure the angle measures are measured in a unit called degrees. Just like you can measure your height in inches or in centimeters. There's more than one measure of units for length. We have more than one measure of unit for angles. So we have degrees that we're going to be using for now. We'll also get into some units called radians later. But just like, for example, if you measure your height in feet, you could subdivide feet, right? There are 12 inches in a foot. So just like that, there are degrees, and then you can have smaller divisions of degree, and so you could have a minute. And so there are 60 minutes, this little symbol, the single, so it says 60, and a little single apostrophe means a minute. So there are 60 minutes in 1 degree. And then taking minutes and breaking it up, we have seconds. Seconds use double apostrophes, and that's 1 second. This is 1 minute. And there are 60 seconds in 1 minute, or there are 3,600 seconds in 1 degree. Okay? So you should be able to convert those. So for example, if I give you this symbol, 23, that's degrees, 15 minutes, and 53 seconds. So this is just 23 degrees, 15 minutes, 53 seconds. All right, so we don't write out these words, instead we use these symbols. So the degree symbol you're probably used to, but minutes and seconds. All right. So let's work with converting some of these. So we have degrees, and so these are more they were useful more in the past. Now that we have decimals, we can be very precise with decimal portion of a degree, but we still want to be able to convert between them. Okay. So convert 17.89737 degrees to degrees, minutes, and seconds. All right, so we take the whole part away, so that's going to be 17 degrees. And so we put the decimal part in our calculators. So put this, see if I can get my calculator going here. We take the decimal part, so 0.89737. So put just the decimal part in your calculator. And then that is degrees, but we want to know, like we know 17 degrees, this is a fractional part of a degree. I wonder how many minutes that is. So we're going to take the degree. Remember, 1 degree is 60 minutes. So I'm simply going to multiply that by 60. And that gives me that decimal degree is 53 minutes, 53.8422 minutes. So we're going to say, all right, we got 53 minutes. So now what we want to do is take away the whole part of it. So subtract 53 from that, and that just gives us the decimal part. So this is the decimal. This is a little bit less than 1 minute. Now we want to multiply that by 60 in order to get the seconds. All right, so, and we'll round that to the nearest whole seconds. So 51, and the double apostrophe means seconds, if that makes sense. All right, so start with the original thing, get rid of the whole part, take the decimal, multiply that by 60. Again, take away the whole part, take the decimal part, multiply it by 60. Okay, let's try the next one. Let's go in reverse now. So this is degrees. We want to turn it, degrees, minutes, and seconds. We want to turn it into decimal degrees. So remember, what is this? This is 11 degrees plus 30 over 60 degrees plus 18 seconds over 3,600. And so that's going to be degrees as well. So now we have them all sort of in degrees. Remember, we had degrees. How do we decimal degrees? How do we convert it to minutes? We multiplied by 60. So now we have the reverse process. We want to go back to degrees. We want to go from minutes to degrees. We divide by 60. Okay. And so when you put all that just into your calculator, you'll get something like 11. Well, we knew that part. 11 point, and then it's this stuff. 505 degrees. Okay. It doesn't really say what to round to, but all right. So now here we have a degrees, minutes, seconds, and we're going to add that to another degrees, minutes, seconds. So it makes sense that we add the minutes together, the degrees together, the minutes together, and the seconds together. And let's do that. So I add the degrees, that's 11 degrees. I add up the minutes, that's going to be 83 minutes. And then I add up the seconds, that's 76 seconds. Now the problem is, of course, I can't have 76 seconds. This would be like saying, how tall are you? Well, I'm 5 foot 13 inches, right? We never say I'm 5 foot 13 inches because 13 inches is already over a foot. So we would take the 12 out of here and move it, and we would say, oh, I'm 6 foot 1, right? 6 foot 1 inch, not 5 foot 13, right? We don't do that. So we got to do the same thing here. So that 76 is too big. We got to turn it into something less than 60. So we take the extra 60 and make it an extra minute. So this, we subtract 60 from this, and that leaves us 16 seconds. And we add this, of that 60 seconds, we get one more minute. So we now have 84 minutes, 11 degrees. But now we got to do the same thing for 84. 84 is too big. We can't have bigger than 60. Well, we wouldn't have 60. Can't have bigger than 59, really. So we subtract 60 away from this. So we still have 16 seconds. So we take 60 away from this, we get 24 minutes. And then that turns our 11 into, right, because the 60 minutes create 1 degree, so that increases by 1. All right, so this is our final answer when we add those. All right, so let's try subtracting this. Now this one's going to be, try doing this really, well, you can't really do it with the calculator very effectively. So do this by hand. So I have, let's kind of put it above each other. So we have 90 degrees, right, lightly, because we're going to erase in a second. 90 minus 17 degrees, 26 minutes, 36 seconds. So it's like we're subtracting, let's say we had, 90, and I'm subtracting 27 from it, right? There's nothing to borrow from the 7, right? I mean, I can't take 7 away from 0, so we have to borrow 1. Make this an 8, move one of these over, it now gets 10, add it to the 0, which would make it 10. And now I can subtract the 3 from the 10, right? So we're going to do the same thing. This is a 0 and a 0 here. I can't subtract these. So what I have to do is I borrow 1 from this, and I turn it into 89. And that makes this 60 minutes. But still, I need something here, so I borrow this again. So this becomes 59 minutes, and that 1 minute comes over here, and it's 60 seconds. All right, so now I can subtract. So I subtract 60 minus 36, that's 24 seconds. And I can subtract now 26 from 59, that's 33 minutes. And I take 17 from 89, and that's 72 degrees, okay? So there's kind of like some borrowing you would do if you were subtracting this, subtracting by hand. Okay. Let's move on to something called coterminal angles. Now, we talked about sort of this idea of coterminal angles. These two angles have the same terminal location, right? 135 degrees and negative 225 degrees are coterminal angles. If I took 135 and I subtracted it 360 degrees, so it went over here, and now I'm going to subtract 360 degrees. I would go back here and I would get negative. If I subtract 135 minus 360, I get negative 225. So the coterminal angles differ by factors of 360 degrees. All right, so here 60 degrees, and then if I added another 360. So if I went 60, but then I added another 360 to it, I would get 420 degrees. So 60 degrees and 420 degrees are what we call coterminal. All right, the two angles that have the same terminal side, they're going to differ by factors of 360 degrees, either subtracting or adding 360 degrees. So 15 degrees, what would be one coterminal angle? There's an infinity of these. You could just keep adding 360 or subtracting 360s and get lots of them. Here we're asked to find the least positive, so it means the smallest positive coterminal angle. So you can't get any lower than 15, so you're going to have to add 360 to that. 375 degrees would be coterminal with 15. All right, 800. So you could subtract 360. So let's do that. We have 805, and I subtract 360, and you notice that's 445. That's still too big. We want the smallest possible. Let's try subtracting 360 again, and you can see now it's 85. And if I subtracted 360 again, it would be negative. So the smallest coterminal angle here is 85 degrees. Okay. All right, so negative 135. We want a positive one, so we're going to have to add 360 to this. That gives us 225. Kind of similar to the numbers we were looking at up above. All right, negative 1,440. Again, we would just, that's negative. We want positive, so we're going to add 360. Let's see what we can do here. If I can get this somewhere where you can see. We have, let's start with negative 1,440, 1,440. And then let's just add 360. It's still negative. Add another 360. Add another 360. And add another 360. And so that's 0. So technically it says the least positive. 0 is neither positive nor negative. So we would still want to add 360 degrees to that. So 360. Yeah, 0 is a coterminal angle with it, but it asks for the least or smallest positive. 0 is neither positive nor negative. All right. Quadrantal angle. So that is an angle whose terminal side is on the x-axis. So we saw a couple of these before. So this is a coterminal angle. 90 degrees is coterminal. Negative 180 is coterminal. 270 is coterminal. 360 is quadrantal, not coterminal. All of those are quadrantal angles, which just means that they end on the terminal side of the angle is either on the x-axis or the y-axis. Okay, so these are examples of them. All right, angular velocity. There is a video that I posted on Google Classroom, a YouTube video. It's only about, 2 minutes long, something like that, of a record player. And it shows the idea of angular velocity. So this is probably something totally new to you guys. You've never thought about angular velocity. You've thought about velocity, and you've thought about, speed or velocity, rate, rate times time equals distance, and rate is being like the velocity. So velocity is the distance traveled over time, the time spent. So if I drove 100 miles and it took me 5 hours to do it, then I drove an average of 20 miles per hour, right? So velocity is just distance traveled, how far you went from point A to point B, and then divided by the time it took you to go from A over to B, right? So with angular velocity, it's how many degrees you've rotated through divided by a set number of time. So we use omega, which is a Greek letter, to talk about angular velocity. So it's like a rate, but it's, instead of distance divided by time, it's going to be the angle, how many degrees you pass through in a set amount of time. So just like rate times time equals distance, in this case, omega times time equals the angle. How much of an angle did we sweep through, rather than how much distance did we travel, okay? All right, so, so a record player is spinning a record at 45 RPM. So RPM stands for revolutions per minute. So in 1 minute, the record rotated 45 times. It's a standard speed on a record player. There are a couple standard speeds, but it's one of them. That's why old records are sometimes referred to as 45s. So you guys probably didn't grow up with records, but your parents know what a 45 record is probably. So a 45 record, it's a smaller record, and it's named 45 because of the speed. If you spin the record at the right speed, then the sound or the music coming out of it sounds correct. If you turn on the record player and the speed is too slow, then it sounds like this. And then if you had it too fast, then it would speed up and it would talk like this. So RPM is just the revolutions per minute, RPM. All right, so assume that a bug is sitting on the very edge of the record. Through how many degrees does the bug move in 12 seconds? So we have this record, and it's spinning, and there's a bug on the outside edge of the record. Now the thing is rotating at 45 RPM. And then we want to think about through how many degrees does the bug move. So let's say the bug, let's just say the bug starts in standard position, and then this record is rotating. Let's assume it rotates. I don't know what way. Honestly, I don't remember which way the record player typically rotates, but let's assume it's rotating in the positive direction. And so it's going to rotate and go through a certain number of degrees in that 12 seconds. And that's what we want to calculate, is what was the degree that was traveled. So let's think about omega. Omega is the angular velocity, and it's given to us as 45 RPM. So let's write that as a unit, revolutions per minute. All right, we want to know how many degrees it goes through. So we want to convert this using dimensional analysis. So we want one revolution. So one full revolution is 360 degrees. So we want to do a dimensional analysis, convert these dimensions. Revolutions are upstairs. I want one revolution downstairs. That's a V, revolutions. And then 360 degrees goes upstairs. So my revolution cancels with my revolution. So now we have 360 degrees per 1 minute. And then we multiply that by the 45. Now we want, our units are not in minutes, but in seconds. So we want to convert our angular velocity. We want it in degrees, not per minute, but degrees per second. So we want to do another conversion. So how many minutes are in how many seconds, right? That kind of thing. So minutes are downstairs, so I need minutes upstairs, and I need seconds downstairs. So 1 minute equals 60 seconds. These are seconds and minutes by time, not the degrees up here. So you just got to be careful that you're keeping your units straight. All right, so minutes cancels with minutes. So what are the units that are left? Degrees per second, and that sounds kind of what we want, right? We have seconds here, and we have, we want to know angles, how many angles we pass through. All right, so the angle, so if we look at this, we want to take omega and multiply it by the time, and that will give us our angle, how many degrees we went through. So omega times t, and so our omega, we would want to simplify this a little bit. Let's see, 360 goes 60 and 360, that would be a 6 and a 1. So we have 45 times 6 upstairs. So that is 270. We have, let's make sure we're keeping our units, degrees per second. All right, everything else is left. We had degrees, we have seconds on the bottom, and now we're multiplying that by 12 seconds. Now with these problems, it's kind of important that you keep your units so that you know you're done, right? I mean, so in other words, I know I don't have any more conversions I have to do because my seconds cancels with my seconds, and the only units left are degrees, so I can just multiply that together. All right, so this would end up being 3,240 degrees that this record would have passed through in 12 seconds. Okay? Yeah, I mean, it's spinning at a pretty good rate. In 12 seconds, it went through not quite 10 revolutions, but, you know, so... all right, so just make sure that when you're doing the angular velocity problems, here's the formula for it, so you know what's multiplying or what's dividing to get what. Rate times time equals distance is what we had for linear velocity, normal velocity, but for angular velocity, it's the angular velocity times the time gives us the angle through which we passed. Okay, so that's it for these notes. Here is the homework. This is due next class.